So, in order to run the program, we can run it from the disk. It runs quite fast from the disk on usual computers. This is not a usual computer. It's probably as old as you are, and it's a bit slow. But on your computers, it should run quite quickly. Okay, so we open that directory and run the executable, and we get this screen, which is the entrance screen. The program is designed to run STM microscopes as well, and that's what this bit is about. It's looking for the control systems. It can't find them, and you say, OK. And now it uses the standard Windows type interface to open and close files. So we go to the buttons up here, there's an open file, and finally, it's an opening file. We won't worry about that. Okay. So we have to navigate to where the data is, and it's on the CD under STM-XPS, STM data, and you'll see there are two experiments. The first experiment is we've just put phenol iodide onto the surface on its own. The second experiment, we put some oxygen first, and then put a progressive amount of phenol iodide. We know a lot about oxygen on this surface, and again, that's in the manual, and you can use that information to help you interpret some of the phenol iodide information. Right, so I'll open the experiment, the first experiment, which is phenol iodide. So I just click that once, and you can see in this box down here, you've got a list of files. If I click on the first one, not double click, just single click, and then go to show, in this box it will give us a series of thumbnail images. And so we can choose the images we want to load. And the first thing you'll notice is that each part of the experiment has two images. So if you look at this one here, you can see it's called 10 lanyards with I and 10 lanyards with a Z on the file name. And the reason for that is that the spectrometer, the microscope, records two images simultaneously. Now, with a standard spectrometer, what it would do when you're scanning the surface, you've got two modes of scanning. The first mode is where you move your tip, you keep your tip at a constant height and move it across the surface. And as you know, the electrons are jumping between the tip and the surface. And where there's an atom sticking out, let's go that way, the tip is slightly closer to the surface than before. And because it's a very sensitive function of height, you see current increase. And that's how we get atomic resolution. Now that's a really good mode for getting atomic resolution. It's very useful if you're in a very small, flat area and you want to look at individual atoms. And it's called constant height. The problem with it is that as you scan over the surface, you can see here, we've got these dark lines here. These are step edges, and they're often multiple copper layers. So your tip is scanning along on a nice flat surface, and it suddenly runs into a brick wall. And what will happen is you will knock the end of the tip off and destroy your imaging. Quite often, you then have to replace your tip. So it's good for looking at atoms, but it's not very good for looking at larger areas. So the other mode of scanning is to take your tip, and as you're scanning your tip across the surface, where it starts to see an increase in current as it approaches something sticking out, you move your tip up and then move it down when you get to the other side. And that can cope with a brick wall, it just moves up over it. And that's called the constant current imaging. Now, these two types of images have different purposes. With our spectrometer, it records both simultaneously. So somehow it keeps the constant current and a constant height. We won't worry about how. But they have different purposes. The constant height gives you usually a better image, better resolution. The constant current allows you to measure the heights of things. You can't measure the heights on a constant height. You can only measure height on constant current. I'll come back to that point a little bit later. So what I'm going to do now is I'm going to call up a couple of images and just show you the differences between the two. So I'll choose something in the middle of the experiment. So this is after 80 nanometers. And so I click on the image, and then I tell it to load. And I've loaded the Z image first, and then I'll click on this one, which is the I image, and load that. Okay, I'll minimize the box, the file open box, and there you can see our two images. Okay, now, in fact, this Z image is almost as good as the current image, so in a way this isn't a good example. We're probably going to use everything on the Z image. Okay, so there's your image of the surface. Now you need a few tools to help you analyze it. And the first one you're going to want to use is to measure distances and heights. Okay, right. So to do that, we need these toolbars up here, and you can see this little box that looks like a peak. It's called a profile. And the profile is how you're going to measure heights and distances. Now, in fact, if you click the arrow to the side of it, you'll see there's two types of profile. There's a single profile, which will record the profile on the active image, which is the one with the blue top, or you can use a multiple profile, which will record the image on whichever images you want. So we'll go for multiple for the moment, so I can show you the difference. And I'll choose now those two images to record, and I'll say, OK. Right, so crosshairs appear, so you can choose where the profile is going to start. You can move this later, so it doesn't matter too much, but let's start on this terrace up here. So you click with the left mouse button to start, drag the cursor around, and you can see the profile is developing as we move it. Click with the right mouse button to finish it. If we click with the left mouse button, we get a dog leg. Now, I don't know why you'd want to do that. Obviously, it's useful for somebody, but it's no use to us. We don't want to do that. So, to finish your profile, you click with the right button, not the left button. Something to remember. Okay, there's our profile finished. Now, and you can see the profile is there, and we can move it around afterwards just by grabbing hold of it, clicking on it, and then we can move it. Right, a few things to see. First of all, this is the constant height image, and so you get no height information. You can see here, although we've gone at terraces, we're getting no height information, and if you look on the axis on the left, it's telling you it's nanoamps, not height. So don't report to me height information from this sort of graph. This one is showing angstroms on the axis. That's fine, we can measure height. We can measure distance on this one, but we can't measure height. Okay, so we can see height, so that's fine, but you'll see something else about that. This is a terrace, and we can think of it as a flat terrace, and yet you can see that it's on a steep slope. That makes measuring, for example, step heights really difficult. So before we can really use a profile, we need to flatten the image. We need to do some software manipulation to flatten the image. So before we do a profile, we'll do that. So that's what I'll show you next. So I'll just get rid of this profile now by hitting delete. I don't want to save it. And I'll get rid of this one as well.